Hello and welcome to a journey through my mind and obviously through magnetic fields. Let's start from this branch. What are magnetic fields? Well, by definition, a magnetic field is a region in space where a magnetic force is felt. In a magnetic field, we have magnetic field lines that determine the shape and density of the magnetic field in these different regions. So if we take the magnetic field produced by a bar magnet like this, we have some regions where the magnetic field lines are more spread out, and that will mean that there is a lower strength in the magnetic field in that region. Other regions, particularly close to the poles of the bar magnet, the lines will be closer, and that represents a greater strength of the magnetic field in that region. Also, the direction is important to notice. The direction in a magnetic field line is always from north to south. The magnetic poles of two bar magnets will repel each other when two like poles face each other, and they will attract each other when two unlike poles face each other. Notice in this diagram how the magnetic field lines of two unlike poles near each other are very dense and very close together, and also parallel to one another. Talking about density, we define also the magnetic flux density, and the symbol for the magnetic flux density is B. B is a vector, which therefore has a direction and a size, a magnitude. Coming back to the idea of how spread out or close together the magnetic field lines are, whenever the magnetic field lines are spread out, we will have a lower flux density, but wherever in the region we have closer together magnetic field lines, then we'll have a greater magnetic flux density. The flux density has the units of Tesla, which is this gentleman who discovered this definition, and the symbol for Tesla is capital T, and we define the Tesla as the flux density through a unit area of 1 meter by 1 meter, obviously. So far we've seen how the magnetic field lines in a permanent magnet like a bar magnet distribute in a certain region, but we know that every time there is a current flowing, for example through a wire, there is a magnetic field induced around the wire. So the wire needs to be straight and long, and whenever we have a current flowing through it, the magnetic field lines will distribute in circles surrounding the wire, and the circles will become more and more spread out as the distance from the wire increases. To find out the direction of the magnetic field lines, we use the right hand grip rule, where we put our right thumb pointing in the same position as the current, and the fingers curl up towards our palm, and the direction in which they curl gives you the direction of the magnetic field lines. Also, another convention says that we can represent a magnetic field going inside the page, in this case inside our screen, or coming out from the screen with respectively a cross when they are going in and a spot when they are coming out. And if you apply the right hand grip rule to these two conventions, you can easily find that the direction of the magnetic field lines are clockwise in this case and anti-clockwise in this case. But we also can study the magnetic field lines produced by a single coil. When we have a single coil, the magnetic field lines are closer in the center of the coil, and they will reinforce their effect, and they get more spread out as we move away from the coil. Interesting to note is that if the current flows in this direction inside the coil, what we will have here is this situation where the magnetic field lines are coming outside from the paper, and in this situation you will have that they go inside the paper, and therefore you'll have clockwise magnetic field lines when the wire goes in and anti-clockwise when it's coming out. But we could have multiple coils, which we call a solenoid, where the magnetic field lines are very close inside and they are parallel and they are equally spaced. That means that inside the solenoid our magnetic flux will be uniform. But on the outside, the magnetic field lines of a solenoid look very much the same as the magnetic field lines from the magnetic field of a bar magnet. In 1864, Maxwell made the remarkable discovery that all magnetic fields are caused by particles that are charged and at the same time moving. So how is it that ferromagnetic materials are magnetic and yet there is no current flowing through them necessarily? Well, it's all to do with the structure of the atom. We know that electrons orbit around the nucleus, and therefore each one of these electrons could be a mini coil that produces a very, very small magnetic field. But in ferromagnetic materials, all these orbits in the atoms line up to form a very regular pattern where all the coils reinforce the magnetic effect of each other, hence producing a strong permanent magnet. How do we get them to line up like that? Well, all we need is to immerse our ferromagnetic material inside a magnetic flux. Some very famous magnetic materials are iron, which demagnetizes quite quickly, steel, which stays magnetized once it's been magnetized for a long time, and cobalt and nickel. Well done! In only a few minutes you've revised quite a large topic. Now try to reproduce this mind map and then try to do some questions on the topic. Good luck!